everyone. Let us begin lecture 18. The topic, of course, the explanation of corrosion events on the basis of mixed potential theory. We have talked about cathodic protection, and we have tried to compare the mixed potential theory of two separate modes of cathodic protection. One is impressed current cathodic protection as well as sacrificial anode. There are lot more into the cathodic protection, but will not talk at this particular junction, because our main interest is to see the mixed potential theory to analyze the corrosion events. Now today we will take another situation, the situation where we consider cathode concentration polarization, and then let us see how that concentration polarization affects corrosion rate of metals. So, the situation corrosion of metal when cathodic polarization is concentration controlled. We have already discussed in part 1 corrosion as well as in the beginning of short review on two types of polarization. One is activation polarization and the concentration polarization. In case of activation polarization, if we try to see the for example, for a cathodic reaction, let us say M n plus plus N e equal to M. If we try to see IC variation, this is E equilibrium of cathodic reaction, this is I 0 of cathodic reaction on metal surface. So, here we are considering the cathodic reaction, the same cathodic reaction. So, this is, I could say that instead of C I can write M. Now, if this is the point, I can have activation polarization, which is decided by I 0. So, this equation, which is the Tafel equation, this is the controlling factor. So, and this axis is log I. So, the potential drops due to cathodic polarization. We are talking about cathodic polarization, and this line is nothing but variation of I c. Now, when it is concentration polarization, so that time I will have the effect of concentration polarization at a higher current density. This is also log scale, and in this case again all the factors are same, equilibrium M, this is I 0 M over M surface. Now, if I try to see the polarization, so initially it will be cathodic polarization, cathodic polarization is activation controlled, and then at a higher potential, higher cathodic over voltage, as well as higher cathodic current density, because I could see that the current density is increasing this way, and also over voltage is gradually increasing in both the situations. So, this is neta C increasing, that means farther and farther it is going downwards in the potential axis. Now, as we go from a low current density to higher current density, I am talking about IC, my governing equation initially it will be of course neta C equal to minus beta C log of IC I0. Even I can and that time, since I am putting minus sign, so that time beta C is taken as a mod value. So, that means only the slope value I am considering, there I am not taking negative sign. So, this negative, if I put negative sign here, that suggests that beta C is positive. So, only the value is considered. Only the value is considered. Now, after that we could see, we have already observed that neta C, when it is concentration controlled, the governing equation becomes 0.059 divided by n log of 1 minus I by I L. So, I could say I C by I L. This becomes my equation, and I could see that when I C reaches I L, neta C, which is the concentration over voltage, becomes infinite. So, I can say that this is activation controlled, and this is also activation, but once we go to a very high current density, it will take a dip, flat dip. So, this point becomes I L, and I L equal to I L can be expressed as, which is diffusivity of the ionic species in that electrolyte, n is number of electrons participating in this reaction, F is 1 Faraday, and C0 is the composition, bulk composition of that metal ion, and delta is the boundary layer thickness or the diffusion layer thickness. Now, there could be a situation that the cathodic reaction is in the activation control zone, and there could be situation that cathodic reaction could be concentration control zone. So, one case the cathodic polarization within this zone, that is always in the activation control zone, and another case the cathodic polarization can reach to this, which is concentration controlled zone. So, these two cases, the corrosion pattern of an active metal, or rather active metal compared to that cathodic reaction, can be different. So, that is the situation we are talking about, corrosion of metal when cathodic polarization is concentration controlled. So, the till now whatever situations we have considered, all are within this activation control zone, and we could see that if all the situations, that cathodic reaction as well as anodic reactions are following Tafel equations, that means both are activation controlled. Now, if we try to see the concentration control effect, that concentration polarization effect on the corrosion of metal, the situation could be very different. Now, let us talk about some metal. an arbitrary metal, let us say M. We consider a situation like hydrogen evolution with a so this is going to be my cathodic reaction, and some metal M which is active compared to hydrogen evolution. I will see that, I will talk about that part, minus Ne equal to Mn plus, this becomes my anodic reaction, and here E0 of H2 equal to 0. So, E naught, rather E naught of Mn plus M is less than 0, and of course, in the solution on the electrolyte I can have a situation where E equilibrium, depending on the pH value of that solution, hydrogen evolution can be greater than E equilibrium of metal. In that situation, of course, hydrogen evolution will be the cathodic reaction and metal dissolution will be the anodic reaction. So, let us see what would happen there. Now, if I try to plot mixed potential theory, again this is E volt and this is log I. Depending on the pH value, this is E equilibrium of hydrogen, and let us say this is I0 of hydrogen over that metal surface, and this particular point is E equilibrium of that metal, and this is I0 of metal on metal surface. There could be two situations. Let us see, let us first draw both the cathodic polarization, that means one is activation controlled, another one is concentration controlled. One is cathodic concentration controlled. If we see activation control, it starts with activation control. So, this is my activation controlled. This is my activation controlled, and then at a very, very high cathodic current density, I will reach IL. So, I will have this line which is nothing but IL of hydrogen depending on the pH of the solution. Now, this metal is guided by activation controlled. So, there could be two situations. One situation is this one, the another situation could be this one. Now, when can we have this two situation? This two situation can be possible if beta A is different. So, in this case beta A1 and this is beta A2, which are basically the Tafel slope, and beta A1 is greater than beta A2, the Tafel slope of the anodic reaction. Now, in one case it is cutting in the activation zone, the another case it is cutting in the concentration control zone. Now, when it is cutting in the concentration control zone, the corrosion rate in this situation, the corrosion current density is nothing but IL. but here the corrosion current density. So, this becomes my I core 1. So, here this is E mix 1 and this is E mix 2. 1 and 2, these are two situations when beta A are different in those two situations. In this case, I core equal to I A. Okay. So, I can denote those. Of course, it will be same as I C hydrogen, but in this case I C hydrogen is activation controlled and in this case I L is nothing but concentration controlled. So, I could get two different situations, but when you see this particular incident, now let us say if I follow this one, let us say, okay. If I change the beta A little bit by doing something, some metal surface modification or something, I can change this line, I can change this slope to this or this. Okay. So, I could see that the corrosion current density is gradually increasing. So, if I consider this is 0.1, this is 0.2, this is 0.3. So, I core 1 is less than I core 2 less than I core 3. So, this situation I am getting within the activation region due to change in beta A. However, if beta A is changed within this segment if we change the beta A, let us say beta is changed like this. This is one change, there could be little increase in the change. So, here I could have situation like 4, 5, 6. Now, in this situation if I try to see their corrosion rate of that metal, this is 4 equal to I core 5 equal to I core 6, since all are equal to I limiting. Now, and in all cases corresponding IC1 hydrogen 1 is less than IC hydrogen 2 less than IC hydrogen 3. So, the same situation, because we have to follow the mixed potential theory, where at some mixed potential the rate of cathodic current density, cathodic reaction is equal to the rate of anodic reaction. But in this situation I could see that E mix is changing. So, the E mix values, if I try to see the corresponding E mix value, this is E mix 2, this is E mix 3. So, this is E mix 2, this is E mix 3. So, I could see that E mix, and if I point this one as E mix 1. So, E mix 1 is greater than E mix 2 greater than E mix 3. Fine. So, this is the situation of E mix we are seeing, but when we get to the concentration polarization side, if I try to see the E mix 4, then E mix 5, E mix 6, that means we are talking about these 3 points. So, those are the mixed potential points. Their relation, I could see that this is greater than, this is greater than, this is greater than this. So, that means if we change their position, that means if I change Tafel slope, which can be done by changing the composition of that particular metal, and if those situations are guided by concentration polarization or activation polarization of that cathodic reaction, then I could have 2 different situations. One is set 1, another one is set 2. So, these 2 situations will come across, and in one situation, even if we change the concentration composition of the metal, thinking that we can reduce the corrosion rate by changing the beta value, that means the slope value, but if they intersect with the concentration polarization line or the concentration controlled polarization segment of that cathodic reaction, we will not have almost no change in their corrosion rates. But if they intersect by changing the composition or the surface condition, if we change the beta value, that is slope value, and if they intersect the cathodic reaction in that activation control zone, we can have change in their corrosion rates. So, the set 1 is, I could say, activation controlled corrosion event, and set 2 is concentration controlled corrosion event. And in this case, corrosion rate does not change, but in this situation corrosion rate changes considerably, considering the fact that this axis is in the log scale. So, there will be order of magnitude change, but here everything is cutting the concentration polarization part, which is basically the IL, and that is what the corrosion rate does not change. But remember, we could see the change in the corrosion potential, and now in this concentration side we could see that though in case of 4, situation 4, and if we consider the situation 5, though E mix 4 is greater than E mix 5. So, I could think that situation 4 I could ennoble the metal compared to the situation 5, but even if we ennoble it, still I could say that the corrosion rate does not change, the corrosion rate still remains at IL. So, that suggests that ennobling of metal does not mean that every time it will have decrease in corrosion rate, Of course, in the set 1, place 1, 2 and 3 if we compare 1 and 2, the 1 has got a higher corrosion potential than the 2. So, that time if since 1 has higher corrosion potential and at the same time it is cutting that metal polarization line is cutting the hydrogen polarization line at a lower corrosion rate. So, here ennoblement is taking place, at the same time ennoblement leads to decrease in corrosion rate of that metal. But in the set 2, even if ennoblement takes place, corrosion rate does not change. So, we have to be very careful while considering corrosion events, and that is what we have to understand the graph, polarization graph very carefully. So, we will talk about polarization curve in the next lecture. So, let us stop our discussion here. Thank you very much.